Thank you very much. Good morning, everybody. So yeah, I'm a roboticist. I didn't know exactly when to raise my hand or not raise my hand during the quiz yesterday about whether we're learning optimization or control. But robotics is in a bit of a funny place right now, right? Because we can do things like this, right? This is one of my favorite robot videos of all time from Boston Dynamics. And it's just so good and so impressive. The finale, of course, most of you have seen it, but the finale is worth waiting for here. Okay, so a humanoid robot can do a backflip now, right? And the crazy thing is, I look at that and I say that is incredibly good work. But yeah, we kind of know how to do that. I mean, we know the math that would be required to do a nonlinear optimization, to find a nominal trajectory. We know how to stabilize that with model-based feedback. There's no deep learning happening in that demonstration, right? We sort of understand it's still hard, it's non-smooth mechanics, but the stuff of control works for this kind of problem. That was unfortunate timing. Okay, so, but it's weird that even though we can make robots do backflips, which I can't do a backflip, Ben's working on his backflip apparently, CrossFit, right? But there's other tasks that I really want a robot to do that that I have no idea how to program, right? So having a robot do something useful like make the bed, or make me a salad, or these problems, even tying a shoelace. Like if you watch a human tie a shoelace, even in slow motion for instructional purposes on YouTube, right? It's just so good and so hard, and I couldn't make a robot do that. Okay, so I want to talk today about some of the reasons why I don't know how to do this yet. One of them is that I don't want to just tie one shoe, right? I'd like to somehow be able to tie any shoe. And I'd like to have one controller that kind of ties. I shouldn't have to write a different controller for that shoe and a different controller for that shoe, right? So there's some richness in the specification, which maybe it's just parameter varying control, maybe it's just robustness. I don't know, but somehow I haven't got the tools yet to design a single controller that can tie this shoe and tie this shoe. But there are a few other reasons too that people could talk about. So one thing people talk a lot about, I'm going to use the whiteboard a little bit. I hope that's okay. I thought it'd be a little bit more interactive based on
Thank you.
Good. Okay. Thank me. As long as we can read it and it works, then we'll say it was a good idea. Okay, so one question is, do we have models, right? Maybe tying shoes is hard just because we don't have a dynamic model of it, right? And actually, a lot of people would say that, and a lot of people would quickly turn to black box optimization and reinforcement learning because of that. But I'm not sure. I think for the Atlas backflipping example, we definitely have good models. But I also think we can write simulators that could be high fidelity enough that if I made a robot tie a shoelace in simulation, I would have confidence that I could transfer that to reality, right? So I think that's a good question, but that's probably not the biggest reason why I don't know how to tie a shoe with the robot. I think this task diversity is a really interesting question. The fact that I'd like to have one controller tie a whole, work for an entire distribution of shoes, and I don't exactly know how to write down that distribution or think about distributional robustness over that distribution. But even that, I'm not sure that's the central problem yet, because really tying shoes should be fairly easy, right? I think the amount of control authority that I have relative to the task is high. I think I could be fairly sloppy with my description of the model and the model uncertainty and still be successful. And I think the cases where we've seen RL work well, I think that property is mostly held, is that the tasks are relatively easy in terms of the model doesn't have to be that good. There's another big one, which is that my main sensor for that, maybe I have some tactile sensing also, but vision is a primary sensor for that task. In the humanoid, I'm able to put potentiometers and sensors inside the robot and instrument exactly I have sort of an easy observation task of trying to estimate the internal state of the robot because I've coordinated my sensors appropriately. If I have to somehow infer the state of the world from a RGB input, I think that is a big problem. And really, I want to talk about this a bunch today because I feel like when I started talking to the controls folks a lot, I remember being completely impressed that every time I came up with a problem, they said, yeah, that's just controls. That's just controls. That's systems theory. Systems theory has an answer for that. But as soon as I said camera, people are like, whoa, no. Controls doesn't have anything to say about cameras, right? RGB is just too hard. Yes?
So regarding this input cameras, tying your shoes, can you do that blindfolded, closing your eyes?
Good. So I think tactile and vision are both important. But there's a huge class of tasks, and I'll talk about more that I almost didn't use the shoe tying example because that one's a little iffy.
And I will even flip it around. Like if you don't have tactile, you have numb fingers, it will be very, very hard to do it just based on vision, right?
I'll try to argue by the end that tactile is not so different than vision. So let me get back to that. Okay, so why are cameras such a hard sensor? So let's say I do have a model, which I'll use our standard form, and let's even pretend it's deterministic for a moment, okay? And now my sensor here, right? So what's the problem with cameras as a sensor? Well, my function G in implementation is like a photorealistic renderer with ray tracing and hitting. It's a computer game engine. Yeah. I missed my one plus. Thank you. So G is an extremely complicated function. Yeah. To the point where we don't think linearization is going to be useful here. And I don't typically have gradients available even if I wanted to. So that's one big scary reason, right? But wouldn't it be amazing if we could do something sort of rigorous? As a result of this being complicated and ugly, I feel like a lot of the times everything we've done with perception has defied rigorous understanding. And the success of deep learning here is undeniable, but even the best sort of tracking algorithms in deep learning, it's hard you kind of scratch your head saying, why aren't they using basic concepts from filtering inside the neural network? There's things that are just unsatisfying. So wouldn't it be amazing if we could come up with some understanding, some model where we could do rigorous systems thinking with cameras? And that's a goal for today. And I certainly don't claim to have an answer, but maybe a toy problem that has helped me think about it a little bit more. Yeah, of course.
Are you imagining closing the loop with the pixels, or are you imagining something like a separation principle type thing where you extract something relevant to your state through a perception module that does estimation, then close the loop with that estimated quantity?
That is so just to repeat that, is it direct feedback from the pixels, or are we going to do some sort of estimation? And that is the question of the day. I will say it can be surprisingly good going directly from the pixels. There's one other big problem here is that, let me say, the Lagrangian state is probably not the right state space. So what do I mean by that? So the shoe tying, again, we could argue about, but think of another problem of just chopping onions. So what's the state space of this problem, right? It changed. It changed. What's the cardinality of my state space, right? If I'm trying to use the rigid body mechanics as my model of this, right? Is it the case that I need to think about a hybrid model with splitting events and jump events? And really, does my controller on the fourth cut have to be reasoning about a different state dimension than the controller at the third cut? Are those really so different? Right? I think there's loads of tasks that come up in manipulation where if you're thinking about the Lagrangian mechanics as your sort of underlying state, you're dead in the water, right? If I want to button my shirt, and the first step is to estimate the state of my shirt, right? In order to, it seems like we've just gone down the wrong path, but that is the tool chain that we have most developed, right? Let me stop that. Okay. So specifically to Nicemay's question, I think that we want to contrast full state estimation. I think state estimation can still be super valid, but probably not estimation of the original Lagrangian mechanics state, right? So for instance, your talk, learning an approximate state, could be very relevant. Okay, so the onion is not an arbitrary example. We got sort of obsessed with that one. And there's a student, Terry, who the work I'm talking about today is his first project with the lab. He joined the lab. I've been saying for years that this is a problem. Cameras are hard. Lagrangian state isn't the right state. We have to do output feedback instead of full state feedback. But somehow it's so tempting, especially with a humanoid robot, to build a better and better state estimator. And it's just so hard to break free of that ideology, right? So I use this onion as an example, saying, what if you were to have to control, solve the onion problem with the robot? Maybe that would be an example where we finally admit that we don't have the state space. We don't even know the dimension of the state space, right? And we have to do something more directly from the sensors. For logistical purposes, the first thing I learned is that for logistical purposes, it turns out that carrots are better than onions. The lab smells better, and they're brighter in a camera and stuff like that. So I still like the name onion problem better because that's how I think about it. But it turns out in practice, I recommend carrots. Okay, and then there's also this question of, do we start with handing a big sharp knife and a deep neural network to a robot? And we thought, no, let's start with the second part, which is after you've chopped the onions, you just need to shove them around a little bit. That's already interesting. That already brings up a lot of the challenges. So let me start with the part where you're just trying to take and manipulate piles of chopped things. And to make it a clear problem we can think about, let's say that there's some part of your cutting board where you'd like to move all the objects to. And so the question is, do you have a model of this? How do you build a single controller that is immune to the number of onions, the pieces of the onions, the geometry of the onions, but somehow accomplishes the task? That seems like it should be an easy task, but can we do it with maybe a principled approach? Okay, so this is my toy problem for today. Here is the onion problem. Onion problem, right? The objective, move pieces to a target set. I'm going to parameterize my action space as a bunch of pushes. So you see we've made this sort of custom little, there's a physical one instead of a PowerPoint one, but we've made a custom little paddle, okay? We think of it as a flat paddle. And our action space is in R4, which is just the position at the beginning, the position at the end. And so that defines a vector of a push, and we'll assume that the paddle is always at a right angle to the push. Okay, so it just takes 4 real values to describe the action space of this. What is the
velocity?
Well, good. So that's a question. So this is the actions, and so I'm going to say it's a discrete, complete motion. So I've abstracted my model to a discrete time model, which is at the time scale of a push.
Okay.
So I'm not thinking about the velocity of the paddle. I'm going to start. I'm going to push and stop.
Okay.
And then the image space. We have a process which we take the original image, we calibrate it into a board frame, we threshold it to get a black and white or grayscale image, we downsample it to get a 32 by 32 image because things get big in image space, okay? And then we can vectorize that into a 1024 vector, okay? So Y is this space. Now, we could think about what would x be if we wanted a state space representation, and we'll have a surrogate for that. Let's think about if we wanted to make some sort of instantaneous estimate of what x is. I'll call that the list of points where each p is the Cartesian position of the non-zero pixels. Okay, but that is not a Markovian state in a sense. Like, because these things can pile up, the dimensionality of this can actually change. But it's maybe useful to think about what an underlying representation is. It's just the location of all the carets. Now, once we have a target set, and this system is quasi-static, so we expect it to be fairly. It doesn't have a lot of dynamics in it, right? Once we push, things settle, and we can ignore any sort of long-term effects. And thinking about it just for a little bit, Terry thought the most natural control approach would be to write a control-Lyapunov function for it. So if we think about having a function that we'll call v of x here, which is just the sum of the distances. I'll show you a picture in a second. Sum of the distances of these particles pi from my target set S. Okay? Let me show you a picture to make that clear. So if I have a target set S desired here, okay, and I have a bunch of particles that are inside, they get 0 distance, everything else, I'll just sum that up as a distance. And I'd like to think that if I can go downhill on that function, anytime I push, if I can make that function smaller, then probably being greedy on that sort of a function will ultimately accomplish the task, and maybe even fairly efficiently. Okay, so this is an interesting but nonlinear function. I won't assume much, by the way, about the target set. This example is a box. It could be a non-convex shape. The one thing we will assume, though, is that it admits a control-Lyapunov function, that this admits this function as a control-Lyapunov function. So we'll preclude any strange geometries where the paddle doesn't fit inside and isn't able to push things in without knocking other things out. But actually, for non-trivial shapes, it's a control-Lyapunov function. Okay. Interestingly, if you take that same function, that same control, the Lyapunov candidate here, if you write it in image coordinates, you can write it as a linear function. Okay? So image coordinates is a weird space, right? But if I think about having a distance image now, if I write v as a function of y, or v as a function of the image coordinates, if that's even helpful to think about, I can actually write it as just some image which has the distances, which I'll show you a picture of here. Okay, d is just the distance of the pixels to that space. It's a one-time computed image. If I just Hadamard product that with the original image, then I've computed the same function. Okay, and that now, or a distance function times yk, is just a linear function of the state, of the observations. So that's already interesting a little bit. Okay, but in order to make progress on that, I need some sort of forward model. So what I need next is some y of k is a y of k plus 1 is some function of yk uk. Okay. In general, of course, I need an entire history, but in this case, like I said, it's quasi-static, so the history sort of dissipates, and I think it's fine to look for models of this form. And we were inspired by the robotics literature on visual foresight and visual prediction, and there's good work on trying to do prediction of pushing objects like this, where the robot is self-supervising, it's pushing things around all day long, and then they learn a deep network which will transition from this image to the predicted image. It gets very hard if you try to predict too far into the future, but for one step or so, you can reasonably sort of shift the pixels along. Okay, so the first thing we did is we tried that. We took the deep architectures. Terry banged his head for quite a while. The story was actually kind of funny. So first meeting after this, Terry's come back and says, the deep models work great. Like the test, the training error, test loss, everything is like incredibly good. Okay, but then he put it on the real robot, and this is what happened. It turns out small errors can defeat our control strategy, right? And in practice, when we scrutinized the performance of the deep network, it did do extremely well. And maybe you could just argue we have the wrong loss function, but it did do extremely well. But every once in a while, it would hallucinate a piece of carrot that would appear out of nowhere, or it would evaporate a piece of carrot. That would just, something that it thought was going to be there wasn't there the next frame.
Ross, can I ask, why was that the first thing you tried?
What's that?
Why was
The
it?
deep?
Yeah.
The deep approach? Because I want to be cool, man.
All right.
Right? Yeah, you got it. Yeah. Anyways, so this was a rough lesson for Terry, and he spent some time trying to regularize the deep network to try to encode some basic, some of our basic sort of understanding, induction bias into this. And at some point we had a conversation where we said, what's frustrating is it would be so easy to tell a linear model how to not hallucinate carrots, right? And that started a deeper conversation about how far can we get with visual foresight using just linear models, okay? And thinking a little bit more about it, it's not crazy. Why is it not crazy? Is because to a first order, what this paddle is doing, before it push, I have one image. I've got to take some action. I'm going to get to a next image. To some extent, if I for any one action, I'm basically permuting the coordinates of the image. Think of it as almost like a permutation matrix. Okay, I'm taking pixels from some place and I'm relocating them to some other place. Okay, it turns out asking for a permutation matrix was too strict because things pile up, things pull apart. But maybe that's the first intuition, is that we could ask for a model of the form yk plus 1, ai yk, where we're going to discretize the action space. But for any one action, I sort of can imagine writing it in this sort of form. Okay? And then the biases that we have, a permutation matrix is too much to ask, but asking for it to be a stochastic matrix turns out to be a reasonable thing to ask. Okay? So we start asking, for instance, that the elements ij are positive. And then we could say that the columns of ij are sum to 1. Okay, j. No I, that's good. Okay, so we can ask for it to be a stochastic matrix. And that's a way for us to say, don't bring new particles into existence, don't remove somehow conserve mass, right? Okay, so this is how it starts looking. So we collected a bunch of data, we set up experiments, we set up simulations that can allow us to collect a bunch of data. Each one is an image, stack the images. We now have a least squares problem. We're trying to find the matrix A, subject to an element-wise non-negativity, and column sum constraint, okay? The problem is these are big matrices, right? So A is already an image by an image. So 1024 times 1024, okay? Ultimately, we might want to do that for every possible action. So it turns out solving it as a QP turned out to be very expensive. And then the only way we could do it for the 32 by 32 images was to actually drop the column sum constraint and just solve each row independently. Right, so this constraint is the only thing that couples the optimization between the different rows of A. So you can solve for each row of A independently if you drop that constraint.
Russ, I'm sorry. The sum equals 1. That means that you're allowing just one element in the whole column to be 1, or what?
Nope. So total. I'm saying preserve the total mass, if you will.
But then you're keeping these, they have to be all less than 1, not only larger than 0. If their sum is 1.
That's true.
Okay.
Yeah.
Because you confuse me with discrete.
Only.
0, 1. You know, so.
Oh, I'm sorry. That is. I'm going to have a different A for every push.
Yeah, but how do you keep it stable?
Yep. So, good question. We could certainly add those kind of constraints if we wanted to. I mean, once we have A, but stability isn't a big issue here.
Okay.
Yeah. In fact, our control Lyapunov function is going to do that work. Yes.
Okay. Yeah.
Just a clarifying question. So you introduced the column sum to preserve mass and get rid of hallucination, and now you've said, well, we're just going to throw away the column sum.
Good. It turns out that well, I'm going to show you in a second here, that this actually does a lot of that work for us, the non-negative. And in fact, once we do the least squares optimization and we just evaluate what the columns come out to be, then we actually get things that are almost always 1.
Okay.
And you
Yeah.
can normalize it.
We could normalize it, but we're not normalizing it here.
Okay.
Yeah. I mean, the pixel values are in some range. Yeah. Yes?
The interpretation of this in terms of going to the limit where you have infinite particles and now you're moving around distribution.
That's exactly where I'd like to go. Yeah. I think that's the big question: is do cameras somehow? So okay. Here's another way to say that. Everything becomes linear in high enough dimensions. Are cameras doing that transformation for us, right? It's almost like we're taking the system into a distribution representation, okay? And I'll come back to it in a second.
Sorry.
No problem. So A is big. It requires lots of data to train. So we'd like to not do that too much, right? If I have to do this for every possible action, if I have to push, in lots of different directions, everything's independent, that's super inefficient. But we play this little trick, which is to reduce the action space. We're going to take any push. We'll still discretize the length of the push, but the orientation of the push can be scaled away, and the position of the push. We're going to take the original image, rotate it into the frame of the push, right? And then we're going to backfill it with the original. We're going to take this with a mask, backfill it so there's other particles that were there from some reasonable distribution. Those particles don't move, so it's okay for them to just have the identity transform over there. And we'll get a lot more data for that, because I worry about the amount of data for this approach, right? A is a huge matrix. How much data do we need? This is a big, important trick for us to be able to train fewer A's with less data. Okay, so we tried a bunch of different approaches. So just standard least squares, if I have no constraints, performed, where this is a plot of the test error for a handful of different approaches. We tried some ridge regression kind of constraints. It turns out that having only the non-negative constraint performed the best. And like I said, when we evaluated the columns of A with the non-negativity constraint, they tended to be around 1, very close to 1. This is the deep visual foresight model, the original one that we used with as little adaptation as possible from the paper. It did very well in training error, but with the amount of data we gave it, which was actually 8 times more than we gave the linear models, it was still a little bit, it didn't perform as well in the test error. And then we tried also the deep visual foresight using that same affine transformation trick, so that we could remove the U input to the deep model and just play the same trick of rotating the images, compute the deep model, rotate them back, and that's what we call the DVF affine.
Yeah, but you know why though?
Good. So let me be very clear. I think clearly linear models are a subset of deep models, right? I think I am not saying that this is not going to be better in general or in practice. I think with the amount of data we were able to generate meaningfully, our bias is stronger here.
No, let's look at the affine versus the.
Oh, the affine versus the original?
It seemed like you put in a bit more structure and it actually did worse.
Yeah, no, that is, I don't have a good answer for why that jumped up. Yeah, this is the one that I worry more about. Good. Okay, another cool thing is that, sort of this is just the showing the test error numbers. The cool thing is that A has a nice interpretation, so we can actually also visualize the fits that we're getting out. So because it's just this linear transform, the rows of A are images, right? So you're basically taking an image of A, if I were to reshape it, times the original image. And we can think of that as the receptive field of that particle. Okay, so just by inspection, we could go through and see, is the model learning a reasonable thing? And it turns out that it learns, if I look at the pink value here, which is the pixel whose receptive field I'm visualizing, the receptive field here of this is basically the identity. It's exactly the pixel that would get there for all the places that weren't in the path of the push. It does a very good job of learning the identity transform in the parts that aren't affected. And then the cool thing is, it seems to do, with even relatively little data, it seems to do pretty well in the sense that if I have a push like this, okay, pixels that are here have a receptive field, it basically learns the identity matrix, so the receptive field is exactly that. Pixels that are here, I have more colors of chalk, have a receptive field that is here, but also sort of blurs out along the edges here. And then pixels that are up here have a receptive field that are sort of along the length of the paddle. So by visual inspection of the linear model's output, it seems to be doing a very good job not hallucinating particles and things like this. So the way I think the way to think about this is, to some extent, we're approximating this as an MDP that's unnormalized, right? So you can think about this as a transition matrix that we're effectively learning, right? Y is it like a probability distribution over the pixel space? And the assumption, effectively, that we're making by choosing this linear model is that each of those pixels evolves independently, right? Which is clearly wrong, right? Those particles can bunch up and knock each other and stuff like this. But thinking about this as for each action, there is some transition matrix. If I think about that as a transition probability matrix, then this is basically like learning an MDP. Okay, and we know lots of good tricks for learning the transition matrices. All right, so I've been looking for this toy problem for a toy problem in image space for a while, and actually when I tried to think about it, is there anything that would have linear dynamics or something that would correspond to any real problem? I was thinking about cars that would just levitate through each other and other things, and I just wasn't happy with it. But somehow this turned out to be actually a linear model works pretty well, and we can start asking, I think, more rigorous questions. Clearly, there's natural extensions that if I had a more dynamic task, I could add a history here, okay? But the real big question, I think, is how far do I go with these kind of models, right? And how do I do synthesis, control design for them, okay? And the big question really is what Naisma asked about, is this going to be an output feedback approach, purely, pixels? Or is it going to have an estimation plus full state feedback type approach? And I think it's worth thinking for a minute about how that works. So I think a slight generalization of this would be to learn an ARX model. And potentially linear in inputs too, but I know I made a leap there. And it turns out we've been thinking a lot in the lab about how would you stabilize that sort of controller, and how would you, to what extent can you make formal guarantees on the original system if you're going to do a feedback directly on Y, okay? We do have reasonable ways to stabilize this type of controller of this form. And I think Ben is going to talk more about disturbance-based feedback, so I won't. But given a model of this form, if we want to search over controllers of the form UK is some k times y0, e0, e1 through ek, or let's say, yeah, k minus 1. This is a disturbance-based feedback controller. So I'm going to take my first observation. And then after I have the first observation, I get my next observation. I can figure out after the fact what my error was. And I can certainly write a controller that's just a linear gain on top of those terms that are all available to me at time k. Okay. And it turns out that most of the objectives that we want to write are convex in k. Right? That's the beautiful thing about disturbance-based feedback. Objectives like LQR, or the equivalent of a quadratic cost on the outputs here. Okay, so we started looking at what is it, what can we do with formal synthesis, with convex optimization over k for problems in this form? And can we make any statement if we want to compare that against systems with the underlying state space form, right? The alternative, maybe approach, would be I have a state space model. I'm going to write an estimator potentially. Let's say I have this would be a sort of a generic form of an observer that's trying to, given a known model in state space form, do my visual prediction through a state space model. And I think it's very interesting to stop for a second and think about what are the differences between these two models that are as far away from each other on the chalkboard as I could have possibly managed. I apologize. Right? So I would expect this model to be better in almost every way, in the sense that I could have a more compact representation of A. I could potentially train it with less data, but I have to solve the hard sys-ID problem through the outputs that Naismeh was talking about before, right? I have to find some internal representation X, which is not probably my Lagrangian state, and I need to find A, B, and C from a bunch of data. I think that probably, the long-term approach will probably look more like this. You can think of learning models in the ARX form, I guess, as just being an inefficient, over-parameterized, again, because over-parameterization is cool, Ben, right? Massively over-parameterized version of that is that I can, just learn these directly, right, and not imply any subspace structure, right? Or anything in between. I could have deep features and try to learn, linear models on deep features or other things like that. Okay, but it's interesting now to be able to say, what can I synthesize directly from this?
Russ, there's also one more alternative you haven't mentioned here. You can synthesize K directly on blocks, right? You can do a disturbance. I mean, it's not disturbance based. That's just pure output based, right?
If I did, if you're saying I could try to learn U as KY, or I could optimize
as vectors, right?
Yeah.
No. Yes.
The whole history.
Yeah.
Right. That's the one that is hard.
How is that different? Why is that hard?
Because it's non-convex in K. Yeah.
No, it's convex in K.
You can do Q
You have to-
parameterization and make convex in K.
Which is what the disturbance-based feedback is.
They're basically the same.
Yeah. You have to transform this into disturbance-based feedback to write that. This one's non-convex. Yeah. Okay. So this is interesting if the dimension of X gets much smaller than the dimension of Y, right? And I think that's ultimately where we'd like to go, but it's not where we are just yet. Yeah, cool.
You have that. You can only construct a state space model from that. Then you can do your, like, every ARX model you can convert to a state space model. Then do your model reduction there and you will get your X.
Yeah.
What's wrong with that?
I think we should try that, right? I mean, there's no question, right? So there's a trivial state space realization of that where you have the whole history of y's as your state variables, x, right? If you could compress that in model reduction, I think it should be part of the story, absolutely. SysID model reduction is, I think, the right way to think about it. We haven't gotten that far with it yet. We haven't successfully found low-dimensional x's that represent this. But I completely agree. I think those are the next steps. Okay, and the other, you can also go the other way, which is if you're given linear models of this form and you want to put it into ARX form, you can do that. And one of the things that was a little surprising to me is that Sadra has some results now showing that if I have models of this form and I write feedback in this form, in this disturbance-based feedback, you can still enforce constraints on X if you're very clever about the way you fit A and B and E, the distributions of E, from the state space model. You can still enforce state constraints in an output feedback setting. So for instance, if I want to make sure that X never goes below 0, for instance, it's possible to do that even with disturbance-based feedback in the output setting. And the trick is to find A, B, and E such that you're minimizing the magnitude of the disturbances, which is a hard optimization, but it turns out with some zonotope reduction approximations, it works surprisingly well. And we have a paper about that that's come out recently. Okay, good. So in practice, we don't know exactly how, I forgot to show the experimental results of that. Let me come back to that in a minute. Okay. So how far can you go with this? So Martin, for instance, a long time ago was doing even acrobats, cart pulls, swing ups from pixels, right? Could we have done acrobats, cart pulls, pendulum swing ups from pixels using purely linear models of the input-output map? And it turns out, yes, sort of. For small deviations, it's got a small, just like the region of attraction of a linear controller on the nonlinear system, it has finite a small region of attraction. This one has even sort of a smaller region of attraction. But it turns out if you generate a bunch of data of a pendulum being bounced around its upright position, okay, you learn a linear ARX model to do that, and you do your disturbance-based feedback. Then actually with just linear control, you can stabilize pendula, acrobat kind of things from pixels. Right? And this is something that we can actually think about. We can do proper analysis on. All right, so how well does it work on the real robot? Here's our experimental pusher setup. We've got a KUKA IWA. We've got our RGB camera looking down at the setup. We've got finely diced carrots, no knife. This is the robot in action, maybe. Okay, the target set here is just a small box in the middle of the board, and it sort of works every single time. It's robust to disturbances. If you have a robot video and you want to show robustness, you need a stick. Okay, and it turns out that as I sort of already illustrated, the linear model works well. This is a model that was just handcrafted forward model, which we said that we think the pixels should move roughly in that place. And the affine, the deep models can work very well, but also occasionally get stuck. So if we compare those models not against just the visual prediction, but actually on the total closed loop performance with our control the optimal function in the loop, then you start to see a bigger difference here where the hallucination in the deep visual foresight model eventually kills it. The deep visual affine model does do better in that case and works almost as well. But what's surprising, I think, what surprised me is that the linear model works so darn well. Okay, the switched linear model, right? It's a transition matrix model. Okay, so this is part of a larger story that we've been thinking about, which is trying to use visual feedback to do sort of category level manipulation. So this is a simple controller that was trained with a deep network to manipulate a dynamic task. That's actually a relatively dynamic task. You have to think about writing down the equations of motion for how that shoe flips around around its pivot there. But the rule is that the same controller has to work for all possible shoes, right? And that's a very hard thing to think about. How do I have to make some rigorous uncertainty distribution? This was the aha moment, because that wasn't in the training set. Okay, picking up a plate, but somehow doing it in a way that's robust to visual inputs. This is, like I said, this version is not using linear models. This is a purely deep approach, but I'm trying to bracket the solution, right? I'm trying to find some things that work well in practice, some things that we understand, and try to sort of go back and forth between these two until we understand something, a more principled, reliable way to generate these feedback controllers. But there is something amazing about giving the robot visual feedback. You get a level of robustness that just wasn't available before, right? It's a very compelling demo too. It's like one thing to see the videos, but if you were to come by and sort of knock the hat yourself, it's like, oh, finally a smart robot, and other people are getting these visual feedback things to work now too, and it's super exciting. I think it's going to make everything better as long as we can think rigorously about it. The trick in that particular one was front end, which was learning particular features by training, having a robot basically play with the object a bunch of different times, putting it in a bunch of different angles, trying to learn visual correspondences, just figuring out that this part of the hat in this picture was the same as that same part of the hat in this picture. That allowed you to train these features that then relatively simple feedback on those features worked very well at runtime and gave this category level.
It's still linear feedback on the features you train?
It's not linear, it's an LSTM feedback on that. Yeah, trained from imitation learning. So this is something that works.
Yeah.
It's probably what the solution looks like, but we don't understand it.
Does it have to be an MIT hat?
It even has to be, there's an obligatory demo, even carrots have to ultimately spell MIT. All right, that's 9:50. Can I answer any questions?
Did you plan that question?
No, that was awesome. That was completely awesome. So there's a couple papers up on the website that tell that story. But can I? Yes.
It's supposed to be IHEFP, huh? Now you save that for the group meeting?
Questions?
Russ, I have
Yeah.
a question about so the one thing, I guess I'll be talking a little bit about some of this later, but from pixels is a very nebulous kind of thing. And I feel like if you do the kind of thing where you put a controlled environment and you do thresholding and downsampling,
Totally.
we still call that pixels. I don't know.
RGB pixels are even harder.
Yeah.
I mean, RGB is things that have lighting variations, color variations, and stuff like that. That's the biggest challenge, no question. But I think there's value in finding sort of the limit. What's the limiting case where we can actually understand it, right? What's the toy problem? There should be some extreme where the complexities of RGB drop away, and we can actually think rigorously about it.
The second question,
Yes.
which is that how much do you think that the dynamics matters?
In that task, not.
No.
But that means the task isn't very interesting yet, right?
Okay.
But surprisingly, in lots of things in manipulation, the dynamic, well, disappointingly maybe, I think a lot of the things we actually want robots to do in manipulation, in making a bed, there is a dynamic approach to it, right? But that's probably not the one we want our robots to be doing all the time. There's a lot of things you can do with quasi-static. Yeah, I think having any models.
I guess that's just something for a broader theme of this workshop, because I think this is something that we don't necessarily talk about, is how you couple those quasi-static things with dynamic things and where you don't even need to think about those. I think sometimes when we say control, I mean, that's a lot of things too. Just like learning, there's a lot of things. Control is a lot of things. So I'm not I just want to be clear where the abstractions are happening, not necessarily say one's better or worse.
Yeah. I avoided manipulation for a long time because there wasn't enough dynamics in it. But yeah.
So this is a naive question. So at the beginning you show like you can cut the carrot and put them into a defined area. So I would imagine that's simpler. Like your target function simply just define the area and measure the distance. But in the later you show like you can turn up the head into the thing there, and that's much complicated. Like I can imagine like perform a very complicated task. You have to define your target function, right? That really depends on how you abstract the task, how you represent the task you want to perform, right? So I would imagine that part would be the challenge. How would you solve that problem?
Writing the cost function for things where you only have image-based feedback is often very hard. That would be my quick summary of your question, I think. And for the hats, the way we didn't do that. Instead, we did that implicitly by using imitation learning. So that was just an existence proof that we can write controllers which have the visual feedback, or we can find a few controllers which have the characteristics that we want. I don't consider that to be a mature pipeline, that if you give me a new task, within the imitation learning context, it actually works very well. We could do a new task that if you're willing to do enough demonstrations, it works. If you change the location of the rack, you might have to redo your demonstrations right now. Okay, so that's not a mature pipeline, but it's an existence proof of what I want to work towards. Now, back it up to something where we can write a cost function simply. We can write dynamics. We're trying to go back towards that hat. Yeah?
So, quick question. So, the example you showed is kind of special in the sense that these particles, if you move them, they stay there, so it's kind of static, right? And also, they are not related to each other. So maybe like an opposite end of the spectrum would be like catching a ball. This is very dynamic, right? But there's a lot of correlation between what the pixels are doing and they are not moving independently. So can you comment on are these methods would be implementable to those tasks, or we should really do something very different, or what do you think about it?
I don't worry about the dynamics so much. I think that if I was using billiard ball particles instead of something that stopped, then I would just put more history of images in there, and I think linear models might still work very well. It's the independence assumption is the one that's going to kill me if I have a rigid object that's bigger, but I actually don't know how bad it is, right? So for instance, what if we did a linear model plus some disturbances, right? Some robust linear model. Can I get a rigid object? Is it the case, because the control tasks are so easy, that a rigorous design on a linear plus uncertainty model which captures the limitations of the independent pixels assumption, might actually work as well and have a more reliable synthesis approach than the full taking into account the sort of explicitly taking into account the dependencies between the particles. But we are trying. So we have initial examples of pushing bigger objects and trying to understand exactly if we can fit, like push the whole carrot, right? We've already got the setup. We're trying that exactly now. Yes.
Before I ask this question, I want to issue a warning that it may be very stupid, but it's a basic question that I hope, if it is an intelligent question, that it might open up a discussion here. And that is, what has surprised me about this is that since you are using pixels, that there's been recent research at Stanford and Berkeley in using L1 and L infinity optimization in a Banach space, which is much more efficient for a computer. And have you looked, and is this incorporated within machine learning?
Definitely. People are absolutely looking at lots of different loss functions. Convex optimization, of course, is not the theme, the main theme in machine learning. We're typically looking at representations that do not permit convex approaches, but absolutely that kind of thinking is present.
Well, can you? Why didn't you go that direction?
I would have been fine doing that. I mean, I think that any of the LP sort of metrics on A or B could have been reasonable in this problem.
Mm-hmm.
Having a closed form least squares solution was, I think L2 was a natural choice here. Okay, would it have made it?
Now you could maybe extend it.
He has a non-negativity constraint, which acts like an L1. That will sparsify things.
Right.
There are lots of ways to add
you
sparsify.
can, all his results are in L2.
No,
Yes.
because once you add the ortho constraint, you're changing the geometry. So there's a lot. I mean, there's lots of different ways to get at that. There's lots of different ways to induce.
I guess I'm biased from what I've seen. I haven't had any experience in this, but from what I've seen is the gain in the speed of computation in posing the form that way.
I do think that if you're thinking about big transformations in image space, then at some point computation becomes a premium.
That's all I'm trying to
So absolutely. It wasn't the bottleneck for us, and the least squares worked fine, and we didn't push it harder.
Thank you.
Sure, yeah. Of course, yes.
So you were, at the answer, you started with linear models and then you went to sort of, LSTM. So can you characterize when you think the linear models will fail, or, is there a way to think about which problems cause that?
I mean, I think RGB and other signals, so even for stabilizing nonlinear systems, we sort of expect linear models to work in some regime, and then at some point, the second order terms come in and break you. I don't know if that's going to hold here. It might be that for big rigid objects that we can do small perturbations with linear models, and that would give us an equivalent theory of local stabilization. That would be great. I'm willing to let it unfold. I don't know exactly what it's going to look like. I'm happy to have finally found one example where we could sort of think about it, right? And now we got to work back up.
Great. For the audience, and thanks
Thank you very much.
keeping
Yes.
very much in time and managing the questions.